Hello everyone, I am Lincoln from Singapore University of Technology and Design, and today I will be presenting about our paper titled Distribution-Aligned Diffusion for Human Mesh Recovery. In our paper, we focus on the task of monocular 3D human mesh recovery, abbreviated as HMR. Despite recent progress, monocular HMR remains a challenging task due to depth ambiguity when recovering 3D information from single 2D images and self-occlusion where body parts can be occluded by other body parts. The depth ambiguity and self-occlusion in this task often bring much uncertainty to the recovery of 3D mesh vertices and places a huge burden on the model to handle this inherent uncertainty. On the other hand, diffusion models have become popular as an effective way to generate high-quality samples, starting from random noise via progressive denoising, displaying a strong ability to recover high-quality outputs from uncertain and noisy input data. We observe that for the monocular HMR task, we also seek to recover high-quality mesh prediction from uncertain and noisy input data, and thus we leverage diffusion models to effectively tackle this task. Here is an overview of our distribution-aligned diffusion process, which primarily consists of two parts. The first is the human mesh diffusion process, which is HMDiff for short. We formulate HMR as a reverse human mesh diffusion process to obtain denoised mesh distribution H0 from the noise HK. The diffusion model is shown as the orange part in this figure. Secondly, we also introduce a distribution alignment technique, or DAT for short. Using DAT, we can infuse prior information to guide the initial diffusion steps. DAT is shown in the green part in this figure. Next, we discuss some of the details of a HMDiff framework. Overall, the HMDiff framework consists of two processes, the forward process and the reverse process. In the forward process, to generate intermediate distributions as step-by-step supervisory signals for training, we apply noise to the vertex coordinates of the ground truth H0, while keeping the topology between the vertices fixed. Next, we build our mesh reverse diffusion process based on the DDIM formulation, which reduces the number of diffusion steps required during inference, and also offers a convenient way to jump over k steps to obtain an early prediction to facilitate our DAT. Using this mesh reverse diffusion process, we progressively denoise the input distribution HK into the target distribution H0. We run the reverse diffusion process in parallel n times and obtain n samples of H0 to represent the distribution. However, it can be difficult to recover a high-quality mesh distribution from the noisy input distribution by using only the standard diffusion process. This is due to the high complexity of the dense 3D mesh structure, which makes it difficult to directly produce accurate 3D mesh outputs with a single RGB image as input. As shown in many previous works on HMR, it is essential to also leverage the prior information extracted via pre-trained extractors, such as post information, segmentation maps, and so on, to guide the 3D mesh recovery process. Therefore, we developed DAT to infuse prior distribution information to the reverse mesh distribution diffusion process. Firstly, we extract a prior distribution U that strongly correlates with H0. Here, our prior distribution U is an extracted post-heat map which contains rich semantic and uncertainty information. At the K step, we compute a distribution alignment gradient using U, which guides us to align samples such that after K diffusion steps, the prediction is pulled closer to U and also the target H0. And it does so in a way that does not disrupt the diffusion process. The distribution alignment gradient is shown here. We also introduce an activation strategy for DAT, which deactivates DAT when HK converges to a more compact and high-quality distribution, as shown in the figure here as well. Please refer to the paper for the details. Overall, in our experiments, we find that our proposed method provides good accuracy for HMR on the 3D PW and human 3.M dataset. We also evaluate our method on freehand dataset for human hand meshes, and we also perform well here. Next, we visualize the output using our method and find that our method effectively recovers the mesh even under ambiguity and produces high-quality mesh results. Next, we also visualize our method when applied to a video, where we also produce high-quality results. Lastly, we also observe that our method with DAT converges quickly and smoothly towards the target as compared to the other baselines. For more ablations and visualizations, please refer to the paper and supplementary. This brings us to the end of the presentation. Thank you very much for your kind attention.